In this problem, we will be using our pipe flow equation, which is equal on the left-hand side to P1 divided by gamma plus alpha times V1 squared divided by 2G plus Z1, which is equal to the height of the hole in the pipe, plus H sub P, which is pump head. In this case, we will have alpha equal to 1 because we are assuming turbulent flow, and pump H sub P will be equal to 0 because there is no pump, it's just a straight pipe. On the right hand side, we have P2 is divided by gamma plus alpha times V2 squared divided by 2G plus Z2 plus the summation of K times V squared over 2G plus the summation of F L divided by D times Z squared divided by 2G. On the right hand side, we won't have any pressure because it's a free jet exiting the pipe. We will also assume in this case that alpha is equal to 1 because of turbulent flow. We will also be assuming that velocity in is velocity out, so V1 will be equaling V2, Z2 will equal 0 because we are assuming that the pipe is starting at Z2. It'll just be equal to 0. There are no minor losses, so the summation of K times V squared over 2G will be equal to 0. We will then reduce this problem, and getting rid of all the terms that are reduced or canceled out to get this equation here. We will then move gamma over to the right hand side of the equation. We will reduce this problem down further, knowing that gamma is equal to rho times G. We will rearrange, and then we can input this into the equation and just have rho. The step's not necessary, but it does allow for further simplification. We will then find epsilon, which is the friction factor, using table 8.1 on page 412. And divide this by D and solve. In part A, first thing we'll need to do is find the Reynolds number. So we take the velocity times the diameter of pipe divided by the viscosity. We solve for that. Then using the Moody diagram, we can find our F and then input this into our P1 equation and solve. In this case, P1 is greater than 0, which means water will leave the pipe. In part B, we again solve for the Reynolds number, this time using our second velocity of 0.5, and we solve. And we once again put this into the Moody diagram using our new Reynolds number. Then we can input this new F into our P1 equation and solve. We find in this case that P1 is less than 0, which means air will enter the pipe.